Hi, my name is Steffen Herbold and welcome to this presentation on our data paper, a fine-grained dataset and analysis of the tangling and bug-fixing commits. Initially, we were 3 authors, me, Alexander Trautsch and Benjamin Ledl, but then our group grew and now we are 48 co-authors. Why this happened, you will see on the next slide, and you can find our manuscript which was accepted for publication in the journal Empirical Software Engineering on arXiv. So what is our work about? Our work is about tangled changes and bug fixing commits. This is best understood with an example. So consider a commit where you might fix a null pointer exception. And the developer might see, oh, there's another problem here. And maybe this method, write cache location, is not well named. And the developer, while adding the null check at the bottom of the textual div, also changes the name of the method from write cache location to write cache location if present. This means we have a tangled change in here, that is a tangled refactoring. And for all kinds of software mining tasks, this kind of tangled changes can be problematic, as we will see later. And we were wondering, can we identify for a large dataset which lines actually contribute to the bug fix? Our study is a bit unusual. It was actually one of the first studies in software engineering that was pre-registered. So we submitted our research protocol to the MSR 2020 registered reports track, and now it's actually also the first ever study in software engineering that was pre-registered and is published. So us 3 went ahead, defined our research protocol with the research question, what percentage of changed lines contributes to the bug fix? And based on prior research, we estimated that it's probably less than 40%. And we also wondered if we as researchers can actually accurately identify the lines which contribute to the bug fix. And based on the assumption that we possibly make random mistakes in 10% of the cases, we calculated that we probably fail for around 10.5% of the lines. And then we had another goal, which is very important for us as a research community. We wanted to help create a huge data set with untangled changes, which is important for software program repair, for test generation, for defect prediction, for bug localization, and basically any task that wants to study software bugs accurately. We then set out and said, we need more people. So we published a call for participation. We had fixed requirements that everybody needed to label at least 200 commits. They needed to provide a review of the paper draft. But if they joined us, if they became active parts of the research team, they could become a co-author of our study. We then plan to submit, once finished, to Empirical Software Engineering, where we already had the in-principle acceptance. And through this, we assembled our large team of 48 co-authors you saw at the beginning, and were able to label almost 290,000 lines in 3,500 commits for about 2,200 bugs with our large team of 48 co-authors from 17 different countries located on 5 continents. You may be wondering how we achieved this. Basically, using a web tool. Based on the web version of Visual Studio Code, we present a textual div of a bug fix, where we see on the left-hand side the state before the bug fix and on the right-hand side the state after the fix. For example, in this case, a hard-coded return value of false was fixed by the actual correct return value. People using these tools had 7 options to deal with the labels. So we could assign a bug fix label to a line, we could identify something as a white space change, as a documentation change, as a refactoring, as a change to the tests, or as an unrelated improvement of source code. Or if we were unsure what it was and want to think about the label more, we could remove the label we might have already set. All this was entered in a diff. We could navigate it using your keys, and this was a very efficient process for everybody involved. The data came from the SmartShark database, in which we already had a large curated set of validated bug fixes. So we've just fetched the bugs from there and then further extended the SmartShark data by storing the labels we generated. In such a study, especially with the scale and the diversity of authors, it's vital to ensure the quality of the data. Our approach was that we used 4 raters for each bug. So not only did we label about 290,000 lines, we labeled each of these 290,000 lines 4 times. Then we combined these individual labelings and only assigned a label if at least 3 of these raters agreed. So at least 3 raters needed to say this line is actually a bug fix to assign the label. If it was 2 or less raters, we did not assign a label to the line and say we do not achieve consensus here. We cannot with certainty state whether this line is, for example, contributing to a bug fix or not. And again, we did this for each line individually. So it's possible that within one file, we have labels for some lines because everybody agreed. And in other cases, it was more difficult and we could not achieve consensus. So what are our key results regarding tangling? When we consider all of our about 290,000 lines of code, we see that only about 1/4 of them actually contribute to the bug fix. So that's a very strong message. Only 1/4 of lines changed within bug fixing commits are actually bug fixes. The larger part of code changes are actually changes to tests, which is, from a software development perspective, a good thing, because it means that we not only increase the software quality, but also improve our software quality assurance. The documentation was also often changed as part of bug fixing activities in about 14% of the lines. There were only relatively few refactorings we detected, and relatively few unrelated improvements. So source code changes mostly really focus on bug fixes. There were also many other changes. So we had white space changes. We had changes that, depending on the labeling strategy, were sometimes labeled as test, documentation, or white space, but definitely no code change. And we had code changes where everybody agreed this is not part of the bug fix, but for example, some rated said this is an unrelated improvement, others said it's a refactoring. And on about 9% of the lines, we did not achieve consensus. More on that later. These 25% lines bug fixing, it's on all code. When we change our perspective, the results change a bit. So if we just look on the production code, in this case, all Java files that were changed, then we see that this goes up to about half of the lines. So in production code, almost half of the activity is for fixing the bug. But we also see that documentation and changes are quite common there, but also that our lines without consensus grow up. So if we had disagreements between authors, it was more likely in production code than in other code. So in other code, this was mostly test code, which makes sense, also given the large percentage of test changes we observed. But here, we mostly achieved consensus, so it was only 1.4% of the lines where we did not achieve consensus here. And also other changes like refactorings, unrelated improvements, documentation changes are relatively rare here. When we look at how this looks like within individual commits and not in our overall data set, we observe that when we count the percentage of lines within commits, that most commits actually have a relatively small percentage of changed lines that contribute to the bug fix, and only few commits are mostly about the bug fix. This is again when we consider all code. So it might seem like many commits are not really about the bug fix, even though there are bug fixing commits. However, again, when we restrict our view to production code, this picture changes, and it changes a lot. So when we look at production code, most changes are really about the bug fix. There's a long tail of commits where we have other changes, including commits where most changes in production code are something else. But for the vast majority of commits, it's about production code. So this is a good thing because restricting errors to production code is relatively simple. So for hypothesis 1, let's look at the results. We hypothesize that fewer than 40% of the lines contribute to the bug fix based on the literature. And we can confirm this. So when we consider all code, it's on average about only 25%, so even a lot less than these 40%. But, and this is a strong but, if we restrict our view to production code, the average goes up to about 50%. So in production code, it's really more about the bug fix. Then you might still be wondering about these 8.9% of lines without consensus. So what happens there? We could calculate based on our data that about 9% of mislabels are probably random. So they're not because of active disagreements. From this, we could calculate the number of lines without consensus we would expect. So remember, we assumed that we probably observed 10% of random mislabels at the beginning, so we're even a bit better with 9%. However, we observe a lot more mislabels overall as well as in the production code. So we have a lot more lines without consensus than we can explain by random effects. This indicates for us that the raters actively disagreed. So somebody thought, for example, this is a bug fix, and somebody thought this is an unrelated improvement. And when we looked into the data, this was indeed the most common case of lines without consensus, that we had 2 raters for bug fix and 2 raters for refactorings or improvement labels. What does this mean for our second hypothesis? So can we identify bug fixing lines? If we consider production code, we can do it to some degree, but we fail in about 15% of the for about 15% of the lines, and this is not random. These are non-random disagreements that highlight the difficulty and are a strong indication that you need multiple raters when you want to accurately identify bug fixing lines. So you might now think, oh God, your data is unreliable. So you now have 290,000 lines of code labeled and it's not really reliable. Well, it's not likely as that. So when we consider we have 9% random mislabels, we can say that only 0.9% of lines where we achieve consensus are wrong, assuming that if we don't achieve consensus, it's only sometimes due to random effects, but most often due to active disagreements. This means due to these random effects where we have non-active disagreements, we only have 111 lines mislabeled without consensus. So our data is not unreliable. The consensus labels are reliable, but we just sometimes fail to agree, but we have actively marked this in our data by not labeling the lines. So all labeled data is very, very reliable. The elephant in the room now is, what is the impact on this tangling on data quality? So maybe we have tangling, but we can detect everything automatically, or maybe it doesn't impact applications. To understand that, we distinguish between benign tangling and malicious tangling. So let's first look at benign tangling. Here's an example from the bug fix for Delta Spike 831. Here we see that most lines are about the bug fix. So this is again a null check that was added. And the last line, this is a tangled whitespace change. But a tangled whitespace change is not problematic. We can easily detect this. We can also fairly easily detect changes to comments. We can detect changes to test files. We can, to some degree, detect refactorings automatically. So there's a lot of tangling we can detect automatically. So this is not a problem for any analysis of source code in the end, if it cleans the data based on the state of the art. But there's also malicious tangling. Here is an example from the bug fix of Eagle 491. And what happens here is that a mere typo is fixed within the message of an exception. An E is deleted. The problem is this tangled typo correction in string cannot easily be corrected because sometimes changes within strings are relevant. For example, when a string indicates the field in a JSON file that should be read, then a change there is an actual change to the programming logic. So we cannot just automatically discard string changes. Maybe in the future we are able to detect output string changes and logic string changes, but for now it is at least not done. So what does this mean? If you were to use this data with such a tangled change for a program repair task, you would have additional effort to find the best correction for program repair because you somehow would need to fix this. If you were to run a bug localization and this is the only change in the file, which is the case here, it might mean that you point to this location, but the bug is not really there, so your bug localization would go wrong. And if you do defect prediction and want to identify which software artifacts are defective, you would have a mislabel in your dataset. We calculated which lines were maliciously tangled from our data, and then how this would impact the different applications. In the best case, we can assume that all lines without consensus are actually bug fixing. So we couldn't agree, but in the end, the people who thought it was a bug fix are always correct. When we do that, we find that for program repair, as about 9% of changes maliciously tangled, for bug localization, there's about 7% maliciously tangled, and for defect prediction, it's about 5% maliciously tangled. If you're interested in why these numbers are a bit different, look at the details in the paper. It depends on which part of the data the different approaches actually require. But the best case doesn't seem that bad. It's annoying to have less than 10% of noise, but probably not too bad. But the worst case, that's different. In the worst case, we would assume that all lines without consensus are unrelated. And in that case, the amount of files that contain tangled information is really high. So it's about 1/3 of the files for program repair and bug localization, and even 39% for defect prediction. So the risk in your data, if you do not manually untangle the data, is huge. In the end, from our perspective, this means that most data sets actually require a warning label, because most data sets, with some notable exceptions like defects for J, contain tangling noise, and due to that, conclusions may be unreliable. There is past research on that by Herzig et al., who showed that, for example, defect prediction results can be affected by tangling, or by Mills et al., who showed that bug localization results can be affected by tangling. In our article, you will find a lot more. So this presentation only showed you parts of what we have done. So we have more about the contribution data from our authors. We have something about the impact of a gamification we have, and we consider some corner cases. So please go to our preprint, read the paper. It's really an interesting read. So thank you for watching this video from all of our 48 co-authors. And yeah, we hope you're using our data. We hope you're using our results, and you consider tangling as severe a problem as we do.